Well, today we begin Chapter 5, where the topic is parallels. So, as in all chapters, you should expect initially that we'll get a set of definitions, potentially a postulate as well, and we'll actually absolutely get a postulate. It won't be for a few sections. And then, once we have that in place, we can begin to build the tool set of parallels, which, once added to the tool set that we created in the previous chapter about congruence, you'll find that we can solve many, many kinds of geometrical problems. So, today, definitions. So first of all, of course, we have to define parallel, and the definition should come as no surprise at all. So we say that two lines are parallel when they are coplanar and do not intersect. And of course, we would like to have a special symbol for this because we would like to have a short way to say that two lines are parallel. And that's the symbol that you see between the A and the B. It looks like a pair of parallel line segments, so that's the way that we say that lines are parallel. We can also, of course, have diagrams indicate that lines are parallel. As we've talked about numerous times before, diagrams have their own kind of grammar. Diagrams can speak to us. Diagrams can, for instance, say that line segments are equal in length. Diagrams can also say that lines are parallel. And the way they do that is with the arrows that you see in the diagram on the lines H and J. They say that the two lines are parallel. And of course, we can have multiple pairs of parallel lines in a single diagram. So you see that the two lines that slope downward are parallel because they both have two arrows on them. The lines that slope upward are also parallel because they have the single arrow on them. This is very much like with congruence, say. We can have two line segments with a single hash or two line segments with a double hash or a triple hash. And so indicate that multiple pairs of line segments are equal in length. Now, just to warn you about what diagrams say and do not say, a topic that we have discussed at length before, if we have a pair of lines and they are not marked in the diagram as parallel, and we have been given no information that would allow us to infer that they are parallel, we simply do not know. You can never, not even once, say that two lines are parallel simply because they look it. And this is a perennial danger in geometry, to make unwarranted assumptions simply based upon how a diagram looks. And we'll have to be careful about that here, just as we were with equality of line segments and equality of angle measures. Now, we will very often have parallel segments and parallel rays. Most often we'll have parallel segments. And what it means to say that a pair of segments are parallel is that the lines through them, the lines that contain them, are parallel. So the definitions of parallel segments and parallel rays are parasitic upon the definition of parallel lines. Transversal. So this is perhaps the first really new idea for you. We don't discuss parallel lines just sort of by themselves. We also always, or almost always, introduce another line called a transversal. And all the theorems ultimately that we have about parallels will involve transversals as well. And a transversal is a line that cuts two other coplanar lines at distinct points. So as you see in the diagram, we have two lines H and J, and then a third line T of course for transversal, that intersects H and J, both of them, and intersects them, this is crucial, and intersects them at distinct points. So if we were to have three lines all through a single point, that does not count as a transversal. And it will be very important for us that what counts as the transversal in certain diagrams can be a relative matter. So for instance, in the diagram that you see, of course, we can have lines H and J with transversal T. You notice that we have 2 points of intersection, one at H, one on H, one on J. But we could also take J and T to be our two lines and H as the transversal, because notice that H intersects J and H also intersects T, and it intersects them at distinct points. So it could be the transversal. As a matter of fact, in this diagram, any two lines could be taken as the two lines, and the third line is the transversal. And you might notice, of course, that in this case we have a triangle. So this begins to suggest how it is that our study of parallels could be potentially relevant to our study of triangles, and it will absolutely be. So what do transversals do? Are they important? Well, they create angles, okay? We've said quite a bit about angles. We had a set of theorems just about angles, like, I don't know, the vertical angles theorem, and then of course our study of congruence told us quite a bit about angle measure, for instance. I don't know, the side angle side postulate, if satisfied by a pair of triangles, would tell us that an additional pair of angles in one triangle are equal to a pair of angles in another triangle. So of course we would like our study of parallels to be able to hook into the study of angles that we have done previously, and they absolutely do. And that's what transversals do for us, because transversal make angles. Okay, so we'll get 8 total angles. Since we have 2 distinct points of intersection, we'll get 8 total angles, one on one line, one on the other. And our primary theorems about parallels will concern relationships of angle pairs created when a transversal cuts a pair of lines. So you can see here the 8 angles created when our transversal T cuts the lines M and N. And the final matter that we need to take up is the special names that have been created for pairs of angles in this kind of situation, in this kind of setup. So let's do that. So first of all, interior and exterior. When we have a pair of lines, in this case M and N, cut by a transversal, in this case T, we have the interior angles, the angles in between the 2 lines, and the exterior angles, the ones outside. So in the diagram that you see, the interior angles are 3, 4, 5, and 6, and the exterior angles are 1, 2, 7, and 8. Now, as for alternate and consecutive, we say that 2 angles that do not share a vertex are alternate when they lie on opposite sides of the transversal, and when they lie on the same side of the transversal, we say that they are consecutive. So if you look at our diagram and consider, for instance, angles 3 and 5, they do not share a vertex, and notice that they are on opposite sides of the transversal, so they are alternate. Another alternate pair is 4 and 6. Another alternate pair is 2 and 8, and the final pair is 1 and 7. And as for consecutive pairs, they are also angle pairs that do not share a vertex, but in this case they lie on the same side of the transversal. So for instance, 3 and 6 are consecutive, as are 4 and 5, as are 2 and 7, as are 1 and 8. Now, here are the definitions that we'll use. It sort of puts together the terms that I've already defined for you, and in each case we'll get a special pair of angles. So first of all, alternate interior. If we have 2 lines cut by a transversal, alternate interior angles are pairs of angles that are, first of all, interior, so between the 2 lines cut by the transversal, and alternate, that is on opposite sides of the transversal, and of course do not share a vertex. So in the setup that you see with lines M and N and T, one alternate interior pair is 3 and 5, and the other alternate interior pair is 4 and 6. Consecutive interior. Given the definitions that I presented, you could figure these out with no doubt, but I'll go through it. Consecutive, again, means don't share a vertex on the same side of transversal. Interior means between the 2 lines cut by the transversal. So in this case, we have 2 consecutive interior pairs. The first is 3 and 6, and the second is 4 and 5. Alternate exterior, again, I'm sure you can figure this out. Alternate means they'll be on opposite sides of the transversal. Exterior means that they're not in between the 2 lines cut by the transversal. So in this case, we have 2 alternate exterior pairs. One, of course, is 2 and 8, and the other is 1 and 7. Finally, corresponding. We say that 2 angles are corresponding. The definition will seem rather complex, and then I'll have another way to think about it that makes it very intuitive. But 2 angles are corresponding if they are consecutive with one interior and the other exterior. Okay, so consecutive. They have to be on the same side of the transversal, and then one has to be interior and the other has to be exterior, and of course they do not share a vertex. So if we were to apply that definition, we would find that 2 and 6 would be one corresponding pair, 3 and 7 would be another corresponding pair. You might take a moment to figure out what the other corresponding pair is. Other 2 corresponding pairs are, one is 1 and 5, and the other is 4 and 8. Now, let me present to you another way to think about how to define corresponding angles. It's not as precise, I suppose, but it's very intuitive. If you look where M intersects T, it's as if we have 4 quadrants, like upper right, upper left, and bottom right. And likewise, we have 4 quadrants where N intersects T. And again, roughly they're upper right, upper left, bottom right. 2 angles are corresponding then when they're in the same quadrants, each on their own line. So for instance, angles 1 and 5 are both like upper right quadrant. Angles 2 and 6 are both upper left quadrant. That's a way that a student told me to think about corresponding angles at one point, and I do find it intuitive. All right, that's it. That's all the definitions we need. And then next time I'll actually begin to prove theorems.